In chapter 12, we started out by taking a look at systems and assumed that the systems that we were studying were rigid. That means that no matter how we put the forces on them, they're going to retain their shape. And essentially, rotation, these are static bodies that we're really studying in chapter 12. But in previous chapters, when the torque was not equal to zero, the object would rotate, but all the points on the object, all the points in space, would remain constant relative to some other point on the object. So now we're going to take a look at what happens when forces applied to a system are going to cause the object to change shape. So now we're no longer assuming that this body is completely rigid, that there is some deformability with this object. And really, for every object, no object is completely rigid. No object is completely incompressible. So we're going to see how a force applied over some area, what we call a stress, is going to cause the object to change shape. This is what we call a strain, and how these two different properties are related by something called the elastic modulus. Okay, so let's take a look at some different types of stresses and strains on objects and see how we can classify them. Again, all objects are deformable. We start out by saying, of course, the simplest model for a solid is that all the atoms or molecules in the solid are somehow connected by a bond. It can be a covalent bond, it can be a metallic bond, an ionic bond, it can be a molecular bond. But essentially, these bonds act like springs, and that the amount of deformation that takes place is going to be proportional to the force applied, but also related to how strong these bonds are. Now, in small forces, these bonds pretty much act linearly like the spring and therefore would obey Hooke's law. At larger forces, we begin to have a nonlinear response between the bonds, but eventually the bonds begin to break and the material will fail. So again, it's possible to change the shape or size of an object, actually both, through the application of external forces. And when these forces are removed, if no damage is done microscopically to the object, the bonds will essentially return to their equilibrium points and the object will return to its original shape. We call this type of deformation elastic, that basically when the deformation is temporary and the forces are removed, that the object will rebound to its original shape. Now, again, Hooke's law, which is basically relating the force to the amount of stretch of a spring, the amount of displacement of a string, is a good way to model many of these systems. We basically say that the applied force that we place on a spring, the spring force, is going to be equal and opposite to the amount of deformation that takes place. Actually, the applied force is proportional to K or equal to Kx. The spring's response, the reaction to this, of course, will be negative Kx. So again, thinking about these materials and the spring constant being related to how strong that spring is, how thick that spring is, we can also think about this proportionality constant, the spring constant, which relates the force to the amount of displacement, having an analogy in most materials being related to how strong these bonds are. And obviously, the stronger the bonds are, the more difficult it is going to be to form these objects for a given amount of force. Now, the spring constant, if we graph force as a function of displacement, has a very large slope when K is a very large value. And as K becomes smaller, it takes less force, less applied force, to change the shape of the object, to stretch the spring. Thus, we get a smaller and smaller slope. Okay, so again, let's define a few things. Stress is the force per unit area causing the deformation. Why do we do force per unit area, which is technically pressure? Well, we do this because the thicker the object is, the more bonds are going to be responsible for opposing this deformation. And therefore, it actually makes more sense to talk about how much force we have per cross-sectional area. And thus, we're going to involve more bonds with a greater cross-sectional area. So, the stress is really related to, how much force this material is taking per bond, if you will. Now, the strain is a measurement of the amount of deformation. Going back to stress, not per bond, but basically, cross-sectional area of bond. So strain is a measure of the amount of deformation. How much is the shape going to change? And then again, the elastic moduli allows us to create a constant proportionality between stress and strain, only for the linear regime. At small enough stresses, we will get a linear response. If the stress exceeds a certain amount, we will begin to see nonlinear behavior. Okay, so the elastic modulus depends on the material that we're dealing with. We're going to start out with Young's modulus, which talks about tensile strength. When we try to take a material and pull it like a rope, pull it apart like a rope, we are dealing with, again, this Young's modulus. And again, this is going to be where we think about the stress, how much force per unit area we have, which is measured in pascals. It's the same unit as pressure. And this is going to be proportional to the strain, which we haven't defined yet. In the case of tensile stress, we are going to change the overall length. So how much does the length change compared to the original length will be our strain. And this will be related to the elastic modulus of the material, where tougher materials with a higher strength, materials that are more brittle, will have a larger elastic modulus, which means it takes more stress to get the same amount of strain for that material. So let's start out with, again, this idea of putting a tensile force on a material, okay? When we're trying to pull the material, we're trying to increase the overall length of the material. So we say L0 is the original length of our material, okay? When we apply a force, we think about the force as being similar to the forces on a rope. It is going to pull away from the center of the material, and thus we expect that the length of the material is going to change. For tensile stresses, it should become longer as the force on the individual bonds feels a tension, and they also become larger due to this overall pressure. So again, the elastic modulus here is called Young's modulus. And again, it relates the force per unit area. And again, this force per unit area is newtons per meter squared. How many pascals we are stretching this material by, the overall force divided by the cross-sectional area, how many square meters of material I have across here. And this is equal to the Young's modulus times the change in length divided by the original length. Now, let's take a look at the units here. The stress that we place on this is in units of newtons per meter squared, so that's pascals. The change in length over the overall length makes strain dimensionless. It has no units associated with it. It's just a ratio of how much does it stretch compared to the original dimensions of the material. And then Young's modulus, of course, is the constant of proportionality, so the units have to be the same on both sides. If delta L over L naught, if our strain is dimensionless, then Young's modulus has to have the same units as we have for our stress. So pascals here, and Young's modulus is also pascals. So let's take a look at a typical stress versus strain curve for a material that we are testing. This is a material which will actually deform quite a bit past its linear region. You can see here we have a nice relationship between stress and strain, that this material should be relatively undamaged. Now, obviously, with a lot of cycling, if we create tension, then we release tension, we create tension, defects in the material can create fractures. But for a uniform material, we would imagine that once the stress is relieved, the strain will be reduced to zero. It will take its original shape. But once we go past some point, in this case, we're seeing something called the yield strength. We go past, the material begins to deform permanently, and eventually, at some maximum stress, the actual reaction will be the material will stretch out at a constant rate. The stress is actually reduced. So this is really the ultimate strength. The number of pascals needed to break the material, because if I keep the stress at this level right here, it's in the process of being stretched. It will break after stretching some given amount of strain. So again, here we can see there's a lot of parallel between the spring and this material. There's this linear region where it sort of behaves according to Hooke's law, if you will. There's a linear relationship between stress and strain. And the slope right here tells you about the Young's modulus of the material, or really how much this material will resist deformation. So how do we actually test different materials? This is very, very important in engineering, that we know the strength of our materials and how much they're going to deform under different stresses, and ultimately how much stress I need to put on them before they fail. Well, this device right here, they actually can do this with hydraulic pumps, but you can essentially take a screw right here, rotate the screws, and create tension between this upper beam and this lower beam, which we're going to attach some sample between. Now, this sample right here is going to be bolted in here, and it's going to be the weakest part of this. You don't want the rest of the device to deform. You want this device to be very, very robust. So the amount of deformation in the upper beam and the lower beam is essentially zero, or so negligible it's not going to really create any change here. But we need some way of monitoring the strain. How much does the length of this material change given the stress that we place on it? And we need a way of measuring how much force we're placing on this, because if you take the force and divide it by the area, you get the stress. So here we can see this material which is being tested. Right here, we actually reduced the area. So that's the part of the material that is going to deform the most. And then there needs to be a way of measuring the change in length from one point to another. So again, you can see here's a fairly brittle material, okay? In the material before, this is a very ductile material. It would go beyond its linear realm where it began to deform non-linearly, but then would actually stretch and then finally fail down here. This material is a little more brittle that's being tested here, where we'll actually reach this non-linear realm right here, and then fail at not much more stress above the region at which we experience elastic behavior. And you can see how it failed, had a fracture across here. And obviously at that point, the load cell, which measures how much force is here, is going to drop to zero because there's no opposing force from the material anymore. So again, if stress continues, we surpass what's called the ultimate strength. That's at the point at which the material is going to fail. And again, the ultimate strength is really the greatest stress that we can put on the object without it breaking. For brittle materials, the breaking point is just beyond the ultimate strength of the material. For ductile material, we'll pass the ultimate strength, and then the stress will drop off, as we saw in this previous example, and fail at a greater strain, but a lower stress. So again, here's the yield strength at which the material is no longer linear. What happens in this zone right here where it's nonlinear, probably, depending on the material, if it's a metal, you can have metal ions slipping past one another and creating defects, small fractures showing up in the material. So eventually we get to the point where material can no longer sustain the stress and still remain at equilibrium. So technically what's happening is it's actually beginning to accelerate and move apart, and then it finally fails at a later point. Now, one of the most important building materials, of course, is steel, and steel is an alloy of iron. Steel has so many different uh, alloys that are available. And basically, what happens here is with iron, iron has these metallic bonds that, basically are fairly strong. However, it's very, very difficult to get pure iron that is free of defects. And what happens here is if I add carbon, which is one of the most important alloys of iron, steel, we add carbon there. Carbon being a smaller atom than the steel will actually lock into the metallic lattice and basically acts like a doorstop. It prevents the atoms from slipping past one another, and it makes the steel much more durable than it would be otherwise. And of course, pure iron, if we look at this graph of pure iron, we see that yield strength is fairly small. Its Young's modulus is also very small. It would not be a very good building material. Wrought iron, which was basically iron that still had a lot of impurities in it. Wrought iron, when the smelting process takes place, we don't eliminate all the impurities. So, wrought iron still had a lot of other elements still in there, silica being one of them. Actually has better mechanical properties than pure iron. But again, with the invention of steel, you can clearly see that it is a much better material in terms of overall Young's modulus, also in terms of the overall yield strength. It's a much stronger material. And you can see that mild steel is, somewhat brittle, not very brittle. It's more brittle than wrought iron, but it has a very large ultimate strength and yield strength to it. And of course, we can add a higher amount of carbon into the steel. Mild steel has a lower amount of carbon to make the material even more brittle. You're basically taking this carbon and locking up the metal lattice. So once it starts slipping, it's going to fail. But high carbon steel obviously has the highest Young's modulus, the highest yield strength, the highest ultimate strength, and is a very good material for different applications. Here you can see so many different alloys of steel, and basically, again, carbon is one of the most important impurities that we can alloy iron with to create steel. But there are other materials that also give favorable properties under certain conditions. Stainless steel, we put chromium in it. Nickel alloy steel, that goes without saying, it has nickel in it. And you can see that we can reach, again, very high yield and ultimate strengths by putting these different materials in here. Now, the other thing I have to say is that the annealing process, the process by which we reheat the material and then cool it, will also have a great effect on the steel. If we want a very hard steel, we generally get a very brittle material, which means that it can be subject to fracturing, especially if there's a lot of thermal cycling. So while stainless steel is good for a lot of applications, It's not a great building material because during thermal cycling, it can fracture because of its high brittle nature. Mild steel, although it's not as strong of a material, tends to hold up under thermal cycling much better. But of course, I'm not a material scientist, so I'm not going to pretend I understand all the different functions of the impurities that we add to the steels, or all the different materials that we alloy into the steels. But again, you will hear the term steel, and you should understand that steel is many different alloys, many different chemical compositions, and of course also how the material is cooled has a profound effect on the mechanical properties of the material. Again, high carbon steel, as its name implies, there's a lot of carbon in high carbon steel. Very good for knives because of its high tensile strength. It tends not to lose its edge very easily. It's also sometimes used in cables. Again, you've got to be somewhat concerned about making the cable too brittle, but when we just want a high tensile strength, using higher carbon levels in our steel can result in stronger cables. Mild steel, again, is used in structural components. We don't want the high level of brittle. We don't want the brittle nature as much. No, it's not as strong as high carbon steel or the stainless steel. It's more flexible and, again, less likely to develop fractures during thermal fluctuations. Let's do a calculations here and just see how we might apply Young's modulus, or the equation for stress and strain, to a particular load situation. Let's say that we have this I-beam and we're compressing it along its length. We have a vertical force of 6 times 10 to the 4 newtons on the steel beam. Let's say it has a cross-sectional area of 8 times 10 to the minus 3 meters cubed. That should be meters squared. We want to find the distance that the beam is compressed. What is the maximum load the steel beam could support before failing? So if the length of the beam is 4 meters, and let's say its cross-sectional area is 8 times 10 to the negative 3 meters squared, cross-sectional area is units of meters squared, find the distance that the beam is compressed. So again, we take stress is equal to Young's modulus times strain. We know the force. Okay, the force here is going to be 6 times 10 to the 4 newtons. We know the cross-sectional area, 8 times 10 to the minus 3 meters squared. We can look up Young's modulus for steel. That is 2 times 10 to the 11 pascals. And we're trying to solve for delta L here. So I solve for delta L. And of course, how much we change in length, it will be determined by how much force I have, what the original length was, divided by the resistance to compression, which is Young's modulus, and how thick the beam is, the cross-sectional area. And even for a very, very large force like this, a force of 60,000 newtons, this will only change by 0.15 millimeters. So, you wouldn't notice that change by your eye. It's 150 microns. So it does flex. It does, compress in this particular case, but it's not really an observable compression here. We're well within the linear range of our stress versus strain curve. What would the maximum load that the steel beam could support before failing? What happens if all of a sudden another member of the superstructure of the building failed and now all the loading was placed on this particular beam? Well, here we know that the stress is equal to force divided by the area. The ultimate strength of steel is, or this mild steel, is 5 times 10 to the 8 pascals. And if we look at this, we can say, well, the force that it can take is equal to its ultimate strength times its area. Again, 5 times 10 to the 8 pascals is where mild steel will fail. And with a cross-sectional area of 8 times 10 to the negative 3 meters squared, this beam can take a maximum force of 4 times 10 to the 6 newtons. So in this realm right here, we have a force of 6 times 10 to the 4 newtons. We can take up to 4 times 10 to the 6 newtons, really almost a magnitude of 2 difference there between the two. So, loading that with 6 times 10 to the 4 newtons is well within the realm of what that beam can take by more than a magnitude, almost 2 magnitudes. So we've talked about compression and tension so far. Actually, we mainly talked about tension, and I use compression almost interchangeably with compression. The problem is Young's modulus, when we're talking about steel, the compressive force of steel and its tensile strength are nearly the same thing. So oftentimes we'll use them interchangeably, as I did with the previous problem. That's not so true with materials like stone, as we're going to talk about in a bit. But in addition to what is the tensile strength of the material, what is the compressional strength of the material, there are also other types of stress that we can place on the material. And one of the big ones is what we call a shear force. And this is a little bit different from compression and tension, because compression and tension, the force is directed toward the center of the material. Tension is away from the center of the material. But what happens if I take the two materials, instead of having it normal to the surfaces, I make it parallel to the surfaces? This is what we call a shear force. So for this particular case, and there are other types of stress that we can place on it. We're going to talk about the major ones here: tension, compression, and shear. But the shear strain, again, is the ratio of the horizontal displacement, how much we move the top surface compared to the bottom surface. And the shear modulus is how much strain we have, how much horizontal displacement do we have compared to how much vertical distance that we have. So for instance, if I wanted to calculate the shear strain of a material under a shear load, I would measure delta x, divide that by the height, and that would give me the shear strain. The shear stress would be how much force I apply, or the thickness of the material, the cross-sectional area of the material. And of course, the shear modulus would be relating the strain to the stress by this equation right here. Okay, so again, you can demonstrate shear strain by taking the top surface of the book and pushing it this way. But again, our shear stress is equal to the shear modulus times the shear strain. And again, here is your stress, here is your strain. By the way, notice the way that I've written this here. You'll sometimes see sigma used for the symbol of stress. You'll sometimes see epsilon used for our strain. Okay, so let's do a calculation of that I-beam again. If we think about this, the wind load on a building may cause these I-beams to bend a little bit, and this bending motion does create tension and compression in there, but they also create sort of a shearing motion of this. So calculate the deformation due to lateral wind load on the same beam from the previous case. 9.1 was the previous case. if the beam were 4 meters long. So a vertical steel beam in a building receives a lateral wind load of 5,000 newtons. How far does a beam deform horizontally due to the wind load if we assume that we are only getting the shear strain happening? And how much wind load would be required to get a beam to deform by 1 millimeter in the horizontal direction? So let's do this calculation first. Again, we want to find out the force. The stress is the force divided by the area. So if I multiply both sides by the area, I get my wind load. Okay, so force is equal to the shear stress times the cross-sectional area of the beam times the change in the delta x is going to be the change in the horizontal distance. H is going to be the height of the beam. And we see that for mild steel, its shear stress is 8.4 times 10 to the 10 pascals. Cross-sectional area, 8 times 10 to the minus 3 meters squared. We want to see how much force to move at 1 millimeter. For an 8-meter beam, it would take 84,000 units of force. Okay. How far does a beam deform due to the wind load? Okay, that's the next slide. Here we're calculating for delta x instead of for F. Sorry, I'm doing this backwards. But here we know the height of the beam. We know how much force we're going to place on it. We know the shear stress. We know the area. We simply solve for delta x here. And under that wind load, under a wind load of 5,000 newtons, that beam will only move about 300 microns, about a third of a millimeter. Now that's important because when we think about the building, if it sways back and forth too much, you might have problems with things such as windows breaking, sheetrock cracking. So all of that has to be engineered into the building. You can't make the building completely brittle because what happens is if the steel is too brittle of a material, it might be stronger initially, but thermal cycling, it getting warm, cold, cycling, movement due to different forces, brittle materials tend to get fractures in them, whereas materials which are a little bit softer, actually bend don't break materials might be more appropriate for such a structure. But of course, if the building is moving, and if you've ever been in a high rise during a significant amount of wind, you can physically physically feel the building moving back and forth. And again, because glass is a very brittle material, sometimes you need elastic spacers. You need rubber spacers to not only allow the glass to thermally expand and contract, but also allow the frame to flex a little bit for the windows themselves. So for tension, when we're having something strain under tension or strain under compression, there will be some change in volume. For shear types of stress, for pure shear types of stress, there will be no change in volume during this deformation. The last type of deformation is deformation due to pressure from all sides. In this particular case, we don't have an isotropic force acting on it. We have a force acting in all different directions. And normally this is due to some type of fluid. And the more pressure we put on the surface of the material, the more it is going to strain under that pressure and therefore change its shape and change its volume. So bulk modulus characterizes the response due to this force coming from all different directions. And again, we can imagine a cube originally outlined by this dotted line right here. And as external forces are applied to each side, that volume will decrease as the material is pushed inward. Microscopically, we are compressing the atomic bonds, covalent bonds, metallic bonds, ionic bonds. Under small loads, they pretty much are going to all behave linearly. And as we compress it inward, our volume, which is originally V, will change by some amount, delta V, which is going to be negative. So in this case, we can say that the pressure applied is going to be equal to the force divided by the area. So that is our stress. How many newtons is applied to all sides? That's our volume stress. And the response is we will get a volume strain or a bulk strain where we will decrease in volume. And you can notice there is a negative sign right here to indicate that delta V is in fact negative. So here, delta P, the stress that we place on it, is equal to negative B, the bulk modulus, how many newtons of force it will take over the area to change the material by delta V over V. Okay, it's really the reciprocal of the compressibility of the material. The less compressible it is, the larger the bulk modulus. So let's imagine we have a solid lead sphere of volume 0.5 meters cubed dropped in the ocean, and it goes to the ocean floor 2 kilometers down, where the pressure is 2 times 10 to the 7 pascals above normal atmospheric pressure. Normal atmospheric pressure is about 10 to the 5th pascals. So we're going to go to a much higher pressure compared to atmospheric pressure. Lead has a bulk modulus of 4.2 times 10 to the 10 pascals. What will the change in the volume of the sphere be? So again, here's our equation right here. We know the pressure. We know the bulk modulus, so we can look that up for lead. We know the original volume, it's 1/2 of a meter cubed. And now we want to see how much does the volume change by. So, just plugging the numbers at 1/2 a meter cubed with a pressure of 2 times 10 to the 7 pascals, a bulk modulus of 4.2 times 10 to the 10 pascals, it's not going to change its volume very much. It's going to change its volume by 2.4 times 10 to the minus 4 meters cubed. So we're going from 1/2 a meter cubed to changing, probably about 1/2 of a thousandth of the total volume of this. So, less than 0.1% of a volume change, or negative 240 centimeters cubed. So again, solids have Young's moduli. They can also have different Young's moduli for tension and compression. They have bulk moduli, they have shear moduli. It's really analogous to the spring constant for our spring. Liquids only have bulk moduli, by the way. They will not undergo shearing or tensile stress. If we try to put these types of stress on it, the fluid is just going to flow, okay? They will, instead of elastically rebounding and regaining their shape, because that's what elasticity is. We put a stress on it, and if we're in the linear range, the elastic limit, it's going to rebound to its original shape. Well, if I take a fluid and I move the top and bottom surface, it's going to flow. If I take a fluid and I pull the top and bottom surface away, it's going to flow, okay? They do not elastically rebound. They only will respond to a bulk type of stress. Now, the ultimate strengths of material are really the maximum force per unit area the material can withstand before it breaks or fractures. Sorry, it says fractures, it should be fractures. In stone, they are much stronger in compression than they are in tension. And unfortunately, all I have are sedimentary rocks here. But as you can see here, limestone can take 18 megapascals before failing under tension, but it can take nearly double that in terms of compressive strength. Sandstone, the difference is even greater, depending on what type of stone it is. And again, rocks are just basically easier to fail if we try to put tension on them, like putting a tension on a steel cable or a rope. We never would want to make a cable out of stone, although buildings have been made out of stone for quite a long time. So because of this general weakness in terms of their tensile strength, they fail if we try to stretch them, but they do well if we put them under a compressive load. This has led to us developing different techniques to improve either the material itself or using different techniques to change the geometry so we reduce tensile loads. This is sort of an aside, but reinforced concrete actually has steel bars within it, so that when the concrete is placed under tension, instead of the concrete, which basically acts like a rock, failing under the tensile loads, the steel will take up the tension. And although the steel makes up a much smaller volume of this, it greatly improves the overall strength of the concrete. So reinforced concrete is really concrete with steel inside it. Our bones are pretty much the same way. Our bones have a very high compressional strength owing to the calcium phosphate, which is in them. Okay. However, if it were just mineral that made up of our bones, they would fail very, very easily. You've probably heard of the term brittle bone disease. In this case, the bone is missing collagen. Collagen is a very strong protein, which gives the tensile strength to our bones. So when our bones are compressed, it's the minerals which usually provide most of the strength against compression. Whereas when we try to stretch them, the long polymers of collagen, which are very, very strong due to their carbon bonds, prevent fracturing under fairly good tensile loads. Okay, so here's a problem that the ancients had in building different structures. When you bend a material, when you bend a structure, the side which is curved outward is going to increase its overall length. So it's going to be under tension. If I bend it, the concave part of it is going to be compressed. So the stone will do very, very well, under compression, but it's very, very weak under tension. So if I put two supports on either side of this big stone slab, its own weight will tend to cause it to fail at the center as a fracture develops due to the tension on the underside. So many columns in typical Greek temples, such as the Parthenon, you had to have all these different loads, so you didn't get what are called bending moments in the overlying stone. And this made for a very, very inefficient structure. It's a beautiful structure, but you have to have all these columns spaced very, very close to one another in order to support the overall load on top. And again, for simpler structures, you might have this post and beam type structure where they would have these posts, which would be made out of stone, and then the stone over here. This would be inherently a very weak structure. And in fact, many of the structures would replace this overall top beam with wood, which is weaker than stone under compression, but actually because of the ligand and cellulose, it can have a higher tensile strength, especially for the same amount of mass. So the post and beam type construction was very, very limited, where you had to have a lot of supports very close to one another, or you couldn't have large openings. This, of course, was solved with the semicircular arch. And of course, the Romans are famous for this, but it was actually used in other cultures too. So it may have been invented, simultaneously by different cultures, independently of one another. But the beauty of this is it keeps the stone mostly under compression. And the way that it does this is, if you think about this, here's your keystone at the top, that the keystone, because it's a wedge shape, will create a force that goes at an angle to the neighboring stones, which will then transfer that force along the direction of the arc. Essentially, every stone here is under compression. None of them are under tension. You don't even have to mortar them together because they'll hold themselves in place just from the overall forces. And once again, because stone is stronger under compression than is under tension, this is inherently a much stronger structure. And we can see its use in the aqueducts of Rome. We can see this in three-dimensional structures where you can take an arch and you can actually rotate it in 3 dimensions or 360 degrees to create a dome. So this keeps every single element of this under compression, and thus you don't have to use any novel materials. Of course, the Romans, knew about concrete. They're very adept at using mortar and concrete, but iron, was very difficult to come by, and certainly steel was not being manufactured in any large quantities. So again, this was architecture and architectural engineering using the materials which were available. Of course, this extended into the Middle Ages in Europe with the Gothic arch. And the beauty of the Gothic arch is that you could take this semicircular arch and really raise it up higher to create an even taller opening. And this, of course, was used in the construction of many of the Gothic cathedrals. The only problem with this is, and this may have been the reason why this wasn't popular with the Romans, that by raising it up like this, it actually creates an outward force that wants to tear itself apart. So you had to create this flying buttress support to create an opposing force, because again, the Gothic arch just wants to separate itself apart, because instead of the forces going along this nice arch, they're actually directed this way. They're actually directed down this way. And what that will do is push the walls out.